it's just super cool being able to talk to so many people and make connections with people, throughout the industry and, like-minded people in general.
I'm Manya. I just wrapped up my first year as a PhD student at MIT, and today I'm going to be talking to you about high-performance code. I'm not going to be teaching you how to write high-performance code. Rather, we're going to be talking about using high-performance code. So let's start with the quintessential example. Say, for example, I want to do a matrix multiply, and I find a high-performance implementation of a matrix multiply in some implementation of that cpplusplus interface. So that cpplusplus sgem is doing that matrix multiply for me. That implementation is going to look nothing like the naive triply nested loop you may have written in your first C or C++ class. It is going to give you the correct answer, though. The actual implementation is going to be thousands of lines of extremely hairy and involved code. And this complexity is a direct function of wanting to take advantage of your hardware to the maximum. You can't write high-performance code if you don't understand your hardware. So in my case, this implementation is going to tile its inputs so that the next time you read your input, it's going to exist in the cache. It's going to use vectorized instructions, so SSE, AVX, neon, you name it. It's going to parallelize your code in the case that you have access to a multi-core environment. It's going to utilize cache blocking. So of course, it's going to tile its inputs to take advantage of the cache. But it's also going to make sure that the instruction stream fits nicely within the instruction cache also, and also behaves nicely with the branch predictor. Finally, it's going to exploit some sort of software pipelining. Hardware today can run instructions out of order. They can take sort of advantage of parallelism within instruction streams. And this implementation is going to exploit all of those properties to get you really good performance. The point I want to make with this is that compilers cannot divine these implementations. Even a Herculean instruction selector cannot take that triply nested loop and lower it into these thousands of lines of extremely involved code using some nice compositional set of rewrites on your AST. You need to handwrite this code. And the hardware is evolving. So even if you were able to sort of take these patterns and retrofit them into monolithic machinery like a compiler, hardware is going to change. And if your computation doesn't fit within these patterns, or the hardware itself evolves, you're stuck. In practice, what ends up happening is that these high-performance implementations often get provided through function interfaces. So essentially, you find a library, the way that I did with cpplusplus, and use that function interface to use a fast and efficient implementation of whatever computation you'd like to do. And this is extremely powerful because these function interfaces are opaque. They hide that complexity underneath. And I, as a programmer, don't need to reinvent the wheel that is a fast matrix multiply anytime I want to use it. A lot of libraries do this. So Intel's 1DNN library, the MKL library, the GNU Scientific library, all of these sort of provide high-performance implementations through function interfaces, precisely because you cannot rely on a compiler-like machinery to auto-generate that implementation for you. So let's actually try doing this together. I have a simple computation up on the screen. I'm going to try to multiply two vectors. I'm multiplying a vector with the transpose of another vector, so that's going to produce a matrix. I'm going to scale that matrix with some alpha, going to accumulate into some result, and during my accumulation, I will also scale with some scalar beta. Simple computation, very straightforward. I told you high performance is all about hardware, and here's the machine I'm running on. I'm going to be using the Apple M1. It has the ARM64 instruction set architecture. And turns out the best implementations for this linear algebra style computation that I have live in two libraries. First, the ARM performance libraries. So these are implemented by the folks at ARM themselves. And the accelerate libraries, implemented by the folks at Apple. Let's start off with the ARM performance libraries. Turns out, with the ARM library, I'm super lucky. I find an interface that can do my exact computation. I just need to understand how to work with it, and I'm good to go. For the accelerate library, however, the story is a little bit different. So for the accelerate library, I actually need two functions. One function to do that vector-to-vector multiply, and another to do that beta and that accumulate into the final result. So the accelerate library does not have that nice sort of single function, but I can get by with two functions. Is it really that different from understanding one interface? Not really. But there's a curious case that happens with the performance of these two implementations. The ARM performance library is 30% faster than the accelerate library. The y-axis there is real time, so lower is better. So the ARM performance library is beating out the accelerate library. The question one might reasonably ask is, why is this happening? A good first guess is going to be, hey, maybe the accelerate vector-to-vector multiply isn't really that optimized. In fact, it's the most computationally intensive part of our application. If you screw that computation up, you're not going to get good performance. So I went ahead and implemented just the vector-to-vector multiply and tried to see whether the accelerate implementation is actually worse than the ARM-PL implementation. That's not the case. Barring some noise, they basically sort of match each other quite tightly. And this is honestly what I'd expect. Both these libraries have been optimized over decades by several talented engineers. They're not going to lose that performance on a vector-to-vector multiply. Another good guess would be that there's something interesting happening with the fact that we're actually composing two interfaces together instead of one. It's not really the insides of these functions that make them slow, but in fact that composition that leads to that performance loss. And what I mean by that is that by the time you're ready to do that beta plus A addition, the first element of the intermediate you produced is already out of the cache. So you're going to experience a cache miss, and that's going to be problematic for you. So let's actually test out this theory. You might say, hey, like that beta and that A is actually quite trivial. It's an element-wise operation. Why don't you just go and edit the accelerate implementation to do it for you? The problem is that the accelerate interface is proprietary. I don't have source code access to it. So A, it's closed source, but unfortunately, it's also extremely important because it's one of the only ways you can target specialized undocumented accelerators like the neural engine or the AMX instruction set on your Apple machine. So if you want to take advantage of that hardware, you're bound to this library. Another idea would be, if really the problem with my function is the fact that I'm going to lose performance because of that cache miss, what if I just process my data in chunks? So I just compute little parts of my data, hope that they live in the cache, and by the time that I'm ready to compute that beta and A just on that little part, I'm going to get a cache hit instead of a cache miss. This is actually quite a simple transformation to implement, and I just have it on the screen here. So first, we're going to go over column tiles of our inputs, just going to compute that vector-to-vector multiplication on that tile, going to do that little SAXP operation, the beta and the addition with the matrix A, and then keep doing this until we actually finish the entire output. So that's what I mean by let's process our data in chunks. I want to flag this idea here as fusion. So this is a very old and traditional optimization. And if you've heard of fusion before, you might be used to seeing it sort of in like LLVM, MLIR style, where you basically have one outer loop and you have computations inlined into that outer loop. I don't have inlined computations, but the fundamental idea is the same. Let's compute independent subsets of our output so as to exploit locality. So this is what I'm going to mean by fusion. And turns out, this chunky accelerate is going to get my performance back to me. So locality was actually the problem in our case, and without understanding the source code or without sort of editing it in any way, I was able to get this to work. So the other observation I want you to keep in mind is that even though these functions are awesome and they hide incredibly hairy, complicated code for us, if we naively compose them, we're going to experience losses in locality. And I just showed you how this was bad for performance, right? We just saw the 30% difference. But more importantly, this is going to be bad for energy. So data movement in current chips today dominates energy cost. The cost of moving some data from a local SRAM, like a cache, is almost 500x than computing something using that data. So we really need to care about locality and data movement if we want to write fast and efficient code. Okay, I mean, we've been doing these simple computations, and I did this transformation. I also told you it's not possible for compilers to sort of do this high-performance code for you, but I want to ask a different question now. Was this a simple computation for a compiler? Could we have expected a compiler to come in and rewrite our code so that it can take advantage of this locality. Let's think about this a little bit, and let's actually think about what we did to take advantage of this locality. What we did was we peered into these two functions. We figured out that to compute some part of your esker, you need some set of columns and some set of rows available, which map onto some part of your Saxby. We did this again for some other set of column tiles, and we kept doing this until we actually completed the computation. That's what we did. From the perspective of the compiler, these two functions are just blobs of code, and interprocedural analysis today in compilers is extremely weak. Even if you were to come up with some heroic polyhedral analysis that could suddenly sort of do this interprocedural style thing, I would like to remind you that the code they hide is that hairy code that we saw previously. And in some cases, this sort of like high-performance code is the adversarial case for any analyzer. So like alias analysis, for example, on high-performance code is exceptionally hard. So a compiler today, or with existing machinery, would not have been able to get us that performance. So I told you up until now that black boxing these high-performance implementations was a really good idea because they're opaque, and as programmers, we don't need to worry about what's happening underneath. I also told you that their greatest strength is also their greatest weakness. This opacity results in locality losses, and we want to get that locality back. The question that I asked you was, hey, can a compiler do this today? And the answer was, probably not. The question that I want to spend the rest of my talk discussing is what information can we give our compiler so that we can keep this control and opacity of function interfaces, so that performance engineers can still write whatever they want under these interfaces while making their composition performant, so while taking advantage of locality automatically. I'm going to spend the rest of my talk answering this question. And if you're concerned about the premise of what I've set up or where we're going to be going next, this is a great time to ask questions. So I'm just going to pause for a little bit in case anybody has any questions. OK, awesome. Well, that's really great to know. Cool. So the big idea at the heart of my talk is that we're going to take these function interfaces and add data production and consumption patterns to them. And then, using those data production and consumption patterns, we're going to automatically fuse our computations. By enriching function interfaces, I mean we're only going to mess with the function's signatures, nothing more. And by fusion, I mean we're going to compute those independent subsets so that we can reliably take advantage of locality. So that's the big idea that I'm going to be spending the rest of my talk talking about. All of this has been implemented in a system called Fern. Fern is an open source library written in C++, of course, and it's open source, so you can look at it today. It works for CPUs, but I'm actively working on extending it to other settings as well. It's just a library, so you don't need your own fork of G++ or Clang++ or anything like that to get this fusion capability to work. The flow of Fern today is that you basically write, you give it a set of function compositions. It's going to produce a C++ file that fuses them for you, and then you can link that C++ file into your actual application to fuse. You can imagine sort of adding a JIT flow on top, but that's not what we support right now. OK, so how does Fern work? I just want to make sure we're all on the same page and we understand what the goals of sort of the system are. So this is what an input to Fern looks like. It's a pipeline object which takes in a vector of other objects. So that those v-add are just objects. The function operator is just overloaded, so it mimics a function call. It's just syntactic sugar. That v-add is defined as a child class to a special class defined in Fern. And that's how Fern will understand all of these function calls. You can outright reason about the data flow between these function calls because you're literally sort of manipulating the same object. So getting that information is trivial. What Fern is going to do is it's going to take that pipeline and generate some C++ code. The point of me putting that code up there is not so that you can understand it or you can read it. I just want to highlight some idiomatic parts of that code. So the first thing that Fern will do for you is it will figure out the dependencies between these two functions. In our case, that v-add is just an element-wise vector addition, so the dependencies are trivial. I'm going to be talking about more complicated dependencies coming in the rest of the talk. It's going to query whatever parts of your input are necessary to actually compute that little part of your output, and then it's actually going to perform the computation. The function calls come directly from sort of that pipeline object that we've been talking about. It's also going to generate some set of outer loops so that eventually finishes the computation. It can compute these independent subsets, but it also wants to make sure that you actually construct your final output eventually. So that's the idea of Fern. Fern is basically going to sort of manipulate these blobs of functions and piece them together so that you can satisfy the dependencies of a downstream function call eventually. The second task it needs to meet, and this is related to that for loop up there, is that it's going to eventually compute all of the output. And this is going to work for many libraries. So this is going to work for the Intel DNN library. You can plug functions from that library in. It's going to work for the MKL library, even for databases. So currently, you can also plug an interface to TileDB into Fern or whatever VB database you'd like. And it's also going to work out for other types of data structures that don't mimic the nice sort of like multidimensional array abstraction that we have. So it's a general enough idea that it will even work on trees. I'm not going to be talking about trees much in this talk, but if you have any questions or are interested, ask me a question or just catch me outside. Okay, so here's what we're going to do. I'm going to walk you through a matrix multiply example, and I'm going to concretize what I mean by let's add data production and consumption patterns. Okay, so for the matrix multiply, I have two inputs. I have input A, input B, and eventually some output C that gets computed. I'm going to point at blocks of that output using 4 metadata fields. I'm going to say X and Y point out the start of that block. The length X and the length Y are going to give you the height and the width of that block respectively. By data production and consumption patterns, I mean you can write down that this function is going to produce some block of C, again with reference to those metadata fields. And to produce that block of C, it's going to consume some parts of A and B. So in this case, it needs to consume some number of rows of A and some number of columns of B. Now, you actually want to finish this computation. You actually want to compute the entire thing. So we're going to wrap this thing in an interval node. This interval node takes in sort of that X and that Y, which are variables that actually get used in that compute annotation. And it has a start, it has an end, and it has a step. All of this information is going to be on top of an interface. So you don't really need to understand the fact that the matrix multiply does accumulate, reduction, any of that. You just need to understand how data flows in and data flows out. And the way that you describe how this works is using sort of those metadata fields that I set up previously. One thing to note here is that these sort of data production and consumption patterns are written from the perspective of the output. So when you're writing these, the question you want to ask yourself is to produce some logical piece of my output. What inputs do I need to consume? You don't ask yourself, given some pieces of input, what output I'm going to consume. So this is like an output-first perspective, which is often traditional in many pull schedulers. Let's go through another example together, and I'll try and highlight some interesting parts of Fern through this example. So this is a convolution, and let's just look at the interface. So it has an input, a filter, an argument that determines the stride that you have, and an output. Again, with the matrix multiply example, we're just going to write down what this function is going to produce. So out, with respect to those metadata fields, but to actually write down what it's going to consume, you're going to need to refer to that stride arg, that stride arg that lives within the interface, because that stride arg determines how much data you're going to be eventually looking at for each part of your output. The nice thing about Fern is that this stride arg doesn't need to be statically determined. You don't need to know whether it's 4 or 5. The thing that you need to statically know is what expression is required to compute that stride arg. So you need to basically formulate an expression to figure out what that stride arg is going to be. It can reason about these things symbolically. Again, you're going to wrap them in these interval nodes, and basically that's the convolution interface. You just need to add that information in. Okay. What does this look like in actual code? I know we've been looking at nice pictures and sort of like nice syntax, but I want to actually show you what this looks like in code. So the first thing you're going to do is you're going to write a class which looks something like this. So this is the convolution class. I'm trying to plug in an MKL interface into Fern right now. So to write this, you're going to first, to this class, you're going to need to have an abstract function call class as its parent. So it's basically an abstract class which forces you to define some key interfaces that we definitely need to know to generate code to target this function. The first information that you need to know is what's the function name. So when I'm actually generating a call to it, I need to actually know the name of the function. The second thing it's going to need to know is what arguments does this function take. So this gives you an ordering on the arguments that eventually get called in that function. And we use this information to match up sort of these abstract arguments with the concrete arguments you eventually end up calling your function with. And we'll do a little bit of type checking for you at this point to make sure you are not doing something like sort of entirely crazy. The next thing that it'll need, and this is the core sort of information that you'll have, is you need to get the data relationship. Here, I basically have some boilerplate where I declare a bunch of variables that I'll eventually use in my data relationship. But the actual relationship looks sort of exactly like the thing that I just showed you on the slide before because it is exactly that thing. I just have overloaded the function call operator here to make it look like it's nice and nested. But we've been looking at this the whole while. So that's basically what you need to write down. That's the meat of this class. You can also imagine these being generated by some preprocessor or being automatically generated in the case that compiler machinery can actually figure out these data dependency patterns. So the first thing about Fern is that it basically has a library of these data dependencies. Currently, I have about 30 to 40 functions added to Fern. These range all the way from element-wise ops, so like ISPC implementations of basic vector operations. It has neural nets, like the convolution, the max pool, stuff like that. It has some operations on trees, linear algebra libraries, and also a database has been plugged in. So currently, this is what Fern looks like. One thing I'd also like to highlight is for any function, you just need to do this task once. And once you do it, any user of Fern can sort of benefit from it. You don't need to do it over and over again. The thing that I kind of elided and sort of glazed over was what was happening with this subset decomposition. I just told you sort of there's 4 fields. Let's understand everything with respect to these fields. But there's something interesting happening here as well. So there are certain decompositions that are legal in Fern and certain decompositions that are not going to be legal in Fern. So say, for example, you have a wide rectangle. That's going to be all right. We can understand that. You have sort of this tall rectangle. That's also going to be OK. But what's happening here with this like wholly like sparse thing? How do you understand this kind of decomposition? So there's a restriction in Fern that actually gives it a lot of power. Anytime you write your subset decomposition, you're going to need to make sure that the shape of that sort of like innermost subset is basically the same as the outermost subset. You want self-similar decompositions. And this gives it a lot of power because A, your functions can be parametrized over this sort of like tiny pieces, and B, Fern can come in and sort of like hierarchically decompose your subsets into smaller and smaller pieces because everything basically looks like that outer data structure anyway. A hack to get this type of stuff to work in Fern would be you just basically create a bounding box around it, and then Fern again can sort of understand everything with respect to the fields that you set up. But then your function needs to understand the fact that you're sort of operating on this like sparse, holy thing. So that's essentially a trade-off that we make. I also want to emphasize that Fern only understands what you're doing with these metadata fields. We don't know what indexing arithmetic is eventually going to go in to actually get some data out. We just know what's happening with these fields. So you still own the physical implementation of your data structure. We just logically understand that implementation through these fields. This is why it's also possible to describe pointer-based data structures, for example, trees in Fern. And this is how you add data structures to Fern. Similar to the previous thing, you basically inherit from an abstract data structure class and define some core utilities. So you're going to give us whatever sort of like metadata you're going to use to actually point at those subsets. In this case, it's going to be 4 fields, so x, y, len x, len y. You're also going to give us an interface to query subsets out of a host data structure. So we'll use these fields and call a query function so that we can actually get that subset out of that particular host data structure. We can also operate on views and not materialize everything. But again, your functions need to understand them that they're operating on views. We also have an insert interface, so you can go in and insert subsets of your data structure into the original sort of host outer data structure. And then we also need some alloc data structure, because we're going to be allocating intermediates when we're sort of doing this computation, so we need to understand how to allocate subsets as well. So really, Fern is going to be a library of data dependencies and data structures. And once you do this for some function and for some data structure, you're all ready to write pipelines in Fern. OK, again, before I move forward, any questions, any places I lost you guys? Yes?
What's the minimum version of the C++ language definition required to use this?
So currently everything is implemented in C++17, and I make pretty heavy use of templates and stuff like that. But I think there's nothing fundamental restricting it to C++17. I think C++11 would also very much work. But everything works in C++17 right now. Yes?
Okay, but Nick, you lost me when you told about this self-similarity.
Yes. OK. So let me rephrase it this way. When you're fusing, you're essentially operating on small chunks of your data, right? And you need to take that data and pass it to your function that actually does the computation.
And these have to be rectangles.
So these necessarily don't have to be rectangles. So imagine I have a tree. A legal subset decomposition would be subtrees. So in a matrix, the legal subset decomposition are submatrices, where the subset decomposition basically has the same shape as the outer data structure.
But not a number of elements.
Sorry?
Not the number of elements.
What do you mean by number of elements?
Like submatrix is smaller than the matrix itself.
Yes.
And it doesn't have to be proportionally smaller. It doesn't have to also be a matrix.
Yeah, it doesn't need to be proportionally smaller. It just needs to be like it just needs to be a rectangle. Whatever length, width, height, doesn't matter. You also don't need to fix the length or the width at any point, because all of our reasoning is symbolic. We can just sort of generate symbolic expressions. But that's a great question. The reason why it's useful is because your functions will be operating on things that look like your outer data structure anyway, so you want to have the same shape. And if you have the same shape, then we can come in and sort of like recursively compute subsets of subsets of subsets, and then that gives us a lot of power and variety in what pipelines we can generate. OK, any other questions? OK, awesome. So we're going to try to write a pipeline. I have a pipeline here using sort of that MKL function that I defined. Again, the call operator is just overloaded, so it's not a real function call. It's just going to produce another object out. That input, and I think the input and the output for the conv are both abstract data structure classes, so they're just pointers to that class, the one that I just showed you right now. And basically, Fern is going to consume that pipeline and generate some fused code for you. I'm not going to go through sort of the actual flow of inferring all of the boundary conditions, but I'm just going to walk you through an example. So intuitively, you have some idea of what information you actually need to solve for to get this all to work today. OK, so this is our computation, a convolution, a max pool, and another convolution. I want to produce some element of my convolution there, right? So I'm going to ask myself, hey, to compute this part of my convolution, what input do I need? In my case, this input is actually coming from the output of another function, namely that max pool. From the data dependency pattern, I know exactly what part of my max pool needs to be computed. So I can figure out what part of my max pool needs to be generated for me to produce that part of the convolution. At this step, again, I'm going to ask myself the same question. To produce this subset of the max pool, what part of input needs to be ready? This is coming from that convolution interface, so then I can sort of propagate that data dependency upwards. Finally, for the convolution, I'll ask the same question and figure out it's actually coming from my image. So that's a true input that's being passed into that pipeline. It's not being produced as an output of some other function call, so I can just stop my reasoning here. There's a lot of nuance that goes into actually making these decisions for pipelines of different shapes, but I'm just going to sort of elide that and sort of call it the internals of Fern. Again, if you're interested, you should catch me outside. OK, so I'm going to be able to reason about sort of the little subsets of my computation. And then I also need to make sure that eventually I end up producing my entire output. So I also want to make sure that the convolution essentially gets computed. Also, this act of looking at what input you will need to produce what output sort of maps nicely to that like output first perspective that I was talking about, that you need to write these annotations from the perspective of your output. And Fern is sort of going to figure out all these dependencies, generate a C++ file that you can then link in, and then start going with. Again, the actual details of that thing is not important. I just wanted to show you sort of a sample output of what Fern is actually going to be working with. So for this example, I tried benchmarking our system against the Intel 1 DNN library. So it's a decades-old library, and turns out Intel 1 DNN has a special graph extension. So that graph extension basically looks at function calls, lifts a call graph of all of these functions, and looks for patterns that it can then replace with fused implementations. So they've built some special machinery to do exactly what we're doing right now, fusing computations. And I think especially when you sort of like talk about performance result, it always makes sense to compare sort of with the industry standard with the best. So we're actually able to match Intel 1 DNN performance here. We do slightly better because the actual computation that I have up there doesn't fit into that precise pattern. It only fits onto a subset of that pattern. So we can actually get some better performance out. Everything is normalized to unfused code. So just if you were to do that naive function composition, your code would have run about like 1.2x slower. So just also normalized everything to unfused code. So this is kind of good news. We're matching machinery that people have sort of spent a lot of time building without doing as much work. And also this will work for other types of functions also, like Intel 1 DNN only works for functions that are in that library. We don't need to sort of restrict ourselves to that assumption. Sort of the last thing that I want to talk about, to sort of talk about certain parts of Fern, is how you control properties of fused code. So I told you that the point of fusion was to actually exploit locality benefits. And locality is not architecture independent. It's sort of a non-portable property. This is because the size of your L1 and L2 and sort of your last level cache is going to differ as you change your actual computer. It's also going to change as the arithmetic intensity of your actual function changes. It's going to change as the length of your pipeline changes and sort of the functions that you actually put in that pipeline change. There's also a fundamental trade-off between redundant compute and locality, and sometimes it makes sense to expose those decisions to users so that they can actually control them. We want users to be able to sort of quickly sweep through the possibilities of all of this fused code. They can sort of tell us what properties they would like in their actual implementation, and then Fern can come in and sort of like deterministically and reliably apply those optimizations for them. So we sort of expose an interface to control the properties of the fused code that we're generating. So let's go back to the pipeline that I showed you, just that simple vector-vector pipeline. The first property of fused code that you can control is that you can choose to split your loops into an inner loop and an outer loop. So say, for example, I just have a naive sort of like outer loop being generated. I can split that loop into two parts, into an outer loop and into an inner loop. This is important because this helps you further tile your computation. You can give Fern the information that you want to do the splitting, and Fern will itself sort of figure out how the dependency patterns will change across these function calls. You don't need to go in and sort of redo hairy index arithmetic, which is often error prone. The second decision you can make is you can choose to sort of parallelize your loops. So this is just like a parallel for. In our case, fusion and parallelism actually go like really well hand in hand. One thing that I didn't tell you was all the inputs to Fern are going to be read-only, so there's going to be no databases there. And the outputs are actually computing on independent subsets anyway, so you can write freely to those. So you can add this parallelism, and currently in Fern, this is implemented as sort of as a work stealing algorithm using an open silicon infrastructure. Work stealing turns out is pretty good because the actual sort of iterations of your loop are doing the same work. So this turns out to be good in practice. I also told you that we can sort of reason about all of these variables symbolically. But of course, if you know that information, you can give it to Fern so that it can do the constant propagation for you. And sort of, if it can completely resolve those constraints at compile time, then it will do that. So you can bind some symbolic values to a concrete value. And now I'm going to sort of describe perhaps the most two interesting ways to transform your pipeline, which essentially change the structure of it. So the first thing you can do is you can choose to break up your pipeline. If your pipeline looks something like this, where you're looping over some symbol and you're sort of calling F1 and F2, a break essentially unfuses your pipeline. So you can sort of like separate out your computation of F1 and F2. And this can be useful for many cases. Say, for example, you want to sort of tile that lower pipeline in a different way, parallelize it in an inner loop as opposed to an outer loop. So you can choose to also express these decisions. And secondly, you can choose to sub-pipeline your computation. This is kind of the opposite of a breaking of a pipeline. You're sort of like computing some functions at a finer granularity than you were before. So here I have, again, F1 and F2. I can call that sub-pipelining operator, and then that F2 thing is going to be computed at some finer granularity. All of these scheduling commands basically return handles to your pipelines so that you can choose to do a sub-pipelining, get a handle to that sub-pipeline, and then sort of keep scheduling it over and over again. So this all composes well. The point is that you can just describe these decisions at a high level, and the compiler machinery is in charge of actually making sure that these decisions are respected and correctly applied. And it will just error if it can't reasonably apply this. Yes?
What would be the point of sub-pipelining if the function doesn't take this parameter? The function is specially prepared for sub-pipelining making sense, right?
Sorry, could you repeat that?
Sub-pipelining introduces new argument, y. New parameter, y.
Yes, yes.
So this function must accept that parameter. Otherwise, there's no point of repeating the same computation. These are all functions, they're pure functions.
Okay, I think you're asking that the functions that I choose to sub-pipeline must also sort of meet some sort of restriction or understand that they're being sub-pipelined?
No, they have to depend on this y, and since they depend, they should be sub-pipelined anyway, because how would you get the value y? We don't usually have the flexibility to pipeline functions, sub-pipeline functions.
So I guess I'm not quite sure I still understand what you're asking me, but
You introduce another loop, subloop, right?
yes.
Loop. That loop is going to be over some new parameter.
Yep.
And so this function has to depend on y.
Yep.
Right?
Yes.
It also implicitly depends on x.
Yes. It does both of those things. You're absolutely right. It depends on both x and y. And Fern is in charge of making sure that whatever dependencies it needs to meet, it actually does. So at that sub-pipelining point, you can imagine that F1 produces some intermediate. So it produces some intermediate result. The sub-pipelining F2 is actually going to be operating on little chunks of that intermediate. So it's going to fuse at that finer granularity. So you're absolutely correct that it both depends on x and y. And the compiler machinery is in charge of making sure that it actually generates the correct dependencies for it.
All right, so the difference between the left and right is that on the left side, F2 gets the whole y.
Yes.
And on the right, it gets a chunk, so it can be optimized because maybe in chunks is faster.
Yep. Yeah. It's not sort of an exact copy. You're not basically copying. You're doing a bunch of other rewrites to make sure those dependency information is still satisfied. And actually, this is sort of the point of providing this interface in the first place, because like recomputing these dependencies is kind of a pain for us. For a compiler, it's sort of straightforward if it has that information up front. So it's not a direct copy. It actually is a transformation that gets applied. Okay, awesome. Any other questions? Cool. So it turns out this collection of scheduling commands is enough to start sort of modeling very complicated dependencies in our fused code. So I'm going to quickly describe a computation to you, and I'll show you how to schedule this computation to sort of get the best performance out. So say, for example, you have an input. You're going to look at 3 elements of that input, going to average those elements and compute it in some intermediate. And then you're going to sort of average 3 elements along the y-axis and produce another intermediate. So this is actually a 3x3 box blur. I just separated it out into 2 different stages. And we're going to try to fuse these stages together now. So the actual sort of schedule that Fern is going to run, and I've scheduled it using the scheduling language, is I'm going to actually compute all of this in little tiles, and I'm just going to fuse at the level of those tiles. And each of these tiles is actually going to be computed in parallel. So that's the idea. Does that make sense? Okay. Another thing that I want you to note is that there's actually some interesting features of this thing. There's like overlapping inputs between different calls to that blur y function. So there's maybe some work that you can actually reuse instead of recompute each time you do this optimization. And Fern has logic to sort of try to make these reusing decisions for you. So that's sort of the basic idea. And again, there is sort of a very famous system out there. It's called Halide. And Halide is essentially a domain-specific compiler that will make all of these decisions for you, lower all of this code. But Fern can basically come in, use a Halide implementation underneath, and then start scheduling it in these nice ways. So we didn't need to reinvent all of the infrastructure that Halide had. We just need to understand how sort of the data dependency patterns of those functions worked out. And we match Halide performance really closely also. Again, if you were just to do naive, sort of unfused implementations, you would get like 3x speed up over that. I think that's the maximum speed up we see. One thing that I also want to highlight is that unfused code is both vectorized and parallelized. So the only difference between my implementation and their implementation is that like point of fusion. So in the unfused code, you called vectorized and parallelized functions back to back. So that's what it's normalized to. But the thing that we can do, and then that sort of other systems like Intel 1 DNN or Halide can't, is we can fuse across domain boundaries. We're not really limited to some sort of data structure. As long as you add that interface to Fern, we can start reasoning about the data structure. So here I have an example where I have a database. In my case, it's TileDB. I'm going to read some output from the database and do a simple scientific computation to it. So I'm going to do a sigmoid in this case. Instead of materializing my entire output, I'm just going to materialize sort of those little chunks of the output that I'm going to be performing the sigmoid on. So I'm actually also going to get asymptotically better memory footprint behavior. And turns out you can get speedups over this also. So that unfused implementation is just me calling TileDB and a nice sigmoid function. Our system sort of does that fusion for you. One thing that I like to highlight here is that this sort of strategy only pays off if you have an in-memory database. You can imagine if you were sort of making requests for data over network, the network is going to be sort of the bottleneck, and cache locality is not going to get you any performance back there. So this works out with in-memory databases, not in other cases. Yes?
Sure, no, that's a one-dimensional problem. There's a zero-dimensional problem. Sigmoid function takes just one part.
Yes, yes.
So,
yes. The sigmoid function is, in fact, element-wise. The data that I'm actually reading out from the database, I'm doing it in like little matrices. Right now, it's just like sort of instantiated as this 2D problem. But you can imagine just sort of like a straightforward streaming interface that just streams one element at a time. And these element-wide dependencies are actually sort of the easiest dependencies to reason about. So in this case, this is not where like Fern will give you the best bang for your buck in terms of the automation that we provide. But if you had sort of more interesting patterns, like that stencil pattern I showed you, or matrix multiplications or stuff like that, then you can start using these.
all right. So
Yeah.
So you get a benefit because you essentially compute the sigmoid while you wait for the memory fetch from the database. Am I correct in understanding?
Yeah. So none of this is happening asynchronously. We request some data from the database, and then we sort of stop our computation, and then we perform the sigmoid.
Only through locality.
Yes, this is only locality, nothing more. In fact, I think this data is quite pessimistic because the way the TileDB interface works is I sort of make a query to it. It's going to parse that, going to JIT out code, and then give me that data back. And I've not amortized the cost of doing that sort of query JIT for me. You can imagine sort of having some caching thing that caches the queries that I've generated. So I think this data is pessimistic in that sense because I'm paying the cost of parsing that thing over and over again. You can, if you were to build TileDB or a system like that, knowing the fact that Fern will interact with it, then I think you could have made much, much better decisions. But I don't really go into the guts of TileDB and make those decisions for them. Questions? Okay, awesome. So the thing that I hope to convince all of you is that really the only thing we needed to understand to start fusing these functions together was just those data dependencies. We just needed to figure out what data was being produced when it consumed some part of it. You didn't need to sort of understand the semantics of your computation or anything like that. You didn't need to peer into the guts of your function. Only at that function signature level, you were able to understand this. So for the matrix multiply, we sort of had the rows and columns. Then we had those element-wise dependencies and so on. I also want to shout out my collaborators. So I'm advised by Jonathan and Saman, and obviously they've been very instrumental in me doing this work. So thank you to Jonathan and Saman. Yeah, and thank you to you guys for listening. Any questions you have, I'll be happy to take them. Yes?
So I understand the biggest impact of the performance
Mm-hmm.
improvement is because of the inner loop. Because this fusion actually, this is where you get the most performance.
So your question is that the place where you get most performance is the inner loop. This is true, yes. If you want, so like say for example, you have some like computationally intensive kernel, it really matters whether your inner loop is vectorized or not, whether it has a switch statement inside it or anything like that. This is absolutely true for performance. The trade-off that Fern makes is it says you can own the inner loop however you want. Like as a function, you can just black box these things, but turns out to reason about locality, you don't need to understand the actual details of that inner loop. You can get away with much less information.
But then we have this layered structure of caches in everything.
Yes.
So in theory,
Yes.
think about the dimension of the problem domain in such a way to maximize the use of it. The inner loop will use the first cache level, the outer loop, the second outer loop.
Yes.
Of course, it depends on the dimension, but do you have any control over that?
Yes. So it's possible to sort of, in some sense, like get those loop outside of Fern using sort of that like little outer loop that we generate to complete your computation. And if you want to say, for example, control the precise granularity of fusion, you can choose the scheduling language to say, please bind this variable to this concrete value. You can make these decisions for yourself. You can also choose to tile your outer loop multiple times. You can't sort of peer into the guts of your actual function, but from that outer scope, basically that exposes enough information to start making these decisions. I think this is also sort of like the key thing that makes it all work is I think traditional compiler machinery assumes that to be able to make all of these decisions, you need to understand what's happening in that inner loop very, very precisely. And the thing that Fern shows you is that you can choose to give up that responsibility like outright and still be able to do this performantly. The scheduling language is what helps you what lets you sort of control those decisions with a lot of precision. I would like to add that even sort of when we generate these fuse implementations and all of that stuff, you need to do auto-tuning just for that like cache sizes and all of that stuff. One thing that's true of high-performance code is like things seldom work out according to your intuition. So we actually do some auto-tuning for that code, just trying out different fusion granularities. But it's possible to control that just from Fern. Yeah.
This appears to be a CPU
Yes.
domain-specific presentation, but
Yes.
it's not entirely clear that it couldn't also be extended to GPU
Yes.
computation. Could you speak to that for just a moment?
Thank you so much for asking me that question. So the question was, this works out for CPUs. What about GPUs? I will also add, what about like distributed settings? That's going to matter a bunch. Yes, today Fern only works for CPUs. I'm actively working on some abstractions for GPUs. But to your point, GPUs can outright like start complicating these decisions, right? Because you have limited amount of shared memory and registry resources per thread block. How do we reason about those fusion decisions? Stuff like that. So I'm actively working on it. I have a bunch of ideas related to it. We can talk more if you'd like after, but this is all CPU. True, yeah.
So my question is very similar, but I think about the MPI, like using different computers. Now the challenge is that those computers will not share the same memory.
Yes.
So you can slice the memory into it, and probably like also move the slices back to some storage, right?
Yes. So in some sense, like you can imagine the distributed case mapping sort of one-to-one well on like the CPU case, where you sort of understand, okay, like what data dependencies do I need to actually meet to make sure I'm ready to compute some part of the output. You can just imagine sort of wrapping like a network call over it so that you can move this data around. The complication is the fact that that network call is actually going to be extremely costly for you. Like moving data around in a distributed setting is not free. Well, depending on sort of technology sort of evolved a bunch, but the cost of the network is going to be reasoned about. Figuring out what needs to live where is not going to be a problem because we just had that information today, and we needed that information to even solve the CPU problem. Yeah, the problem is going to be that network calls are going to be expensive.
But those can be dedicated, those can be imputed by the programmer, right? Because we have some knowledge domain, and we know, for instance, that this is the size of the cell I want to put into the one node, one compute node. And you can divide the program domain into cells.
So what do you mean by these can be computed by the programmer?
So okay, I'm thinking about solving differential equations,
Mm-hmm.
and we have the temporal and spatial relationships, and those spatial relationships look a little like convolutions. So we are thinking only about convolutions, and convolutions have this limited domain. And the idea is that you compute one cell like 5 by 5 points, and maybe it's three-dimensional. You would need still data outside of the domain because maybe those convolutions are like 3 cells.
Yes. So this idea of like ghost cells in terms of overlapping stuff. Yes. So even with the examples that I showed you with the stencils and with all of that stuff, that those had overlaps. You can just sort of compute. So the main sort of machinery at the heart of Fern is being able to like infer sort of the bounds of what you will need. If those bounds are overlapping, that's not really a problem, assuming sort of those data structures you treat as read-only. You might introduce races if you are operating on overlapping stuff, but assuming you're just sort of treating them as read-only things, we can just compute those bounds for you and move the data around. So overlaps is not a problem on inputs. It's going to start being a problem on outputs because you don't want to write to the same place at the same time without some synchronization. Yes?
Can this be generalized to graph data structures as well?
Yes. So currently I have some benchmarks that are able to work on trees, for example. I haven't tried doing like traditional graph algorithms yet, but certainly it could be generalized to data structures beyond just NDM arrays. There are some restrictions on operating with graph data structures. So oftentimes graph data structures, say for example, will like produce dynamically sized output. So if you're doing a filter on a graph and filtering out some nodes, you're going to produce you don't know the size of your output up front. That's a restriction. Those types of things can't work with our bounds inference machinery today. There are ways around it where you sort of produce an optional value as opposed to a real value, and then you sort of have this coalescing phase. But yes, graph data structures can work with some caveats.
Yeah, on a related note, you have this constraint here that the internal substructure should have the same shape
Yeah.
as the external one. What would that mean in a graph?
Yeah, so those would just be subgraphs, right? So you can imagine one subset decomposition being, let's take 2 metadata fields, let's take a node, and let's take the neighbors of that node up to some distance. So using just those 2 metadata fields, you can start pointing at subgraphs. So you just need to figure out a strategy to decompose them in terms of these fields, and you'll be good to go.
Arbitrary subgraph without any constraint on shape. Like I don't understand exactly what you mean by shape.
Well,
I get it in the 2D sense, but like,
yeah. For the graph thing, I don't know if it can be an arbitrary subgraph outright, because you need to be able to like Fern needs to be able to query for that subgraph using some collection of things. So you need to parameterize that subset over some collection of things. Yeah, you need to figure out how to decompose it. So one strategy that I recommended was like restrict it to some number of neighbors around some center node. Yeah, but if you have something special in mind, we should just talk about it and work through that example together after the presentation.
yeah, the setting that I was like the context that I was thinking of was GNNs.
Okay, we should talk more about this offline.
I
Okay.
don't know.
Okay.
Thanks.
Yeah.
Have you, during your kind of experimentation, have you found cases where you were surprised that the naive result seemingly was better? I guess I'm trying to think about if I'm using this and I encounter some case that
Yes.
Fern author, should I be like, oh my god, I'm using this wrong, I should keep banging on it, or
Yes. Yes, there are cases where, say, for example, keeping your computation unfused is perfectly fine. So if you imagine a function that already hits the theoretical peak for your machine, sort of artificially increasing its arithmetic intensity by fusing stuff, it's not going to help. Like you stack peak functions that hit peak on top of each other, they're still going to continue to hit peak. There's no need to sort of optimize for data movement in that case. The second case where a system like Fern actually does not work well is in places where you want to fuse over your registers. Because we work with this function interface abstraction, the lowest sort of granularity of reuse that we can exploit is the L1 cache. But if you want to keep something in the same register and sort of move it around a bunch, we're not going to be able to do it through function interfaces. So you're going to need to sort of do that yourself. The nice thing about Fern is if you have something that requires that sort of register style fusion, you can just write that function yourself and plug it into us and we can start using it. So there's always sort of this like black box function escape hatch out there. But yeah, that's a case where you would not want to use a system that fuses via these function interfaces but understands register level reuse. Yeah?
Do you have any experience using Fern for matrix structures which are kind of special in some sense, like symmetric matrices, right? I only access the lower diagonal part of my matrix. Do you have, because then I
Yes.
don't really understand how the substructure thing works, because it kind of varies as you go along the matrix, like the size of the maximum size is different.
Yes.
And B, I guess like a row isn't really a subtriangular matrix.
Yeah. That's a great question. So triangular iteration spaces can work. There's a strategy with which you can sort of describe decompositions of your triangles. So basically, the constraint of wanting to be self-similar is the fact that your functions need to be able to operate on that shape. So if your functions can, say, for example, operate on rows of your output or stuff like that, then that'll be okay. But yeah, you can sort of describe at least triangular iteration spaces, certainly. Yeah.
How does it affect the instruction cache? Because as the code grows, I'm pretty sure that because of all the data dependencies, and everything, it's going to query.
Yep.
And it's going to increase the
pressure on the instruction cache. That's also a great question. So the question is about how does the instruction cache deal with all of this? So say, for example, you're fusing at like extremely fine granularities. If you're fusing at like element-wise granularities, the number of function call you make will just, it'll just be like a crazy number of function calls. So the granularity at which you choose to fuse at also directly impacts the number of function calls you'll be making and how much pressure you're going to be putting on there. So there's actually a sweet spot. You're going to need to do some search to figure out what granularity is going to be best. So there's certainly cases where it matters and you actually want to test it to see what the actual granularity is. Right now, the autotuner that I have is basically a bash script because I just need to sort of loop over these discrete points. It works out well in practice, didn't need anything more complicated than that. If you need that bash script at any point, I'd be happy to share it. Yeah.
One of the nastiest computations out there is the continuous wavelet transform.
Mm-hmm.
And I'm wondering, has anyone on your team tried to wrestle something like this into computing a continuous wavelet transform?
No. I don't think anybody has yet, but I can keep that in mind and look into it and see how that's going to work out.
Normally avoided because they're so computationally intensive in CPU land, but maybe this will help.
Okay. That's a very good suggestion. I will go look into it. Yes.
So the dimensions are dynamic, but what if we know the size of the inner loop in the compile time? Because that compiler could, for instance, do loop unfolding and unrolling.
Yes. So question to your question is, by inner loop, you mean the loop inside the function or the loop that Fern will generate to sort of? Yes. So there's sort of two ways that this works out. What happens is like, I showed you a set of like these scheduling commands. One of them is a bind scheduling command. So you can bind a symbolic variable to a concrete value and sort of Fern will come in and do that constant propagation for you. You can also choose to like take a value and expose it as a template parameter. So when you actually call that function, that's going to do it for you. So both cases end up working out. If you have that concrete information, you can communicate it to us. Okay, I think that's the end of questions. Thank you so much for being here. I'm really excited to be here, and thank you so much for asking such great questions.